Here is a sequence of the first 9 natural numbers. A 3 by 3 reshape gives us a 3-row, 3-column matrix. We define an init set. And mark items in the matrix that are members of the init set. 1 for yes, 0 for no. We'll call this Boolean matrix R. We can embed R in a slightly larger matrix, a 5 by 7 take of R, which pads below and on the right with zeros. We can center our original within this by doing the -2 rotation about a vertical axis, the number 1 dimension of the matrix. And a -1 rotation about a horizontal axis, the 0 dimension of the matrix. We'll call this larger matrix capital R. Here is a vector of 3 matrices. We can see this more clearly if we use a library function which draws boxes around subarrays. Mapping rotate onto 1, 0 and -1 and the matrices distributes the rotation onto corresponding items in the first and second argument vectors. So we see our original 0 rotation in the center and a 1 and -1 rotation on either side. The sequence containing the full outer product of rotations can be performed by iterating over the horizontal rotations in an inner loop and the vertical rotations in an outer loop. And the final neighbor count matrix is done by applying the add operation over the sequence. This is a neighbor count for each cell in our original matrix R. The rules of Conway's game of life are that you have a 1 in the following generation if the neighbor count including itself is 3, or if the neighbor count including itself is a 4 and the original cell was occupied. So first, find the 3's and 4's. The equals x function creates a new function on a matrix that will return a Boolean matrix, where cells are 1 when equal to the given scalar and 0 otherwise. When the equals x function is built on the neighbor count matrix, it can then be mapped to the values 3 and 4. And we're interested in any 3 and a 4 corresponding to an occupied cell, which is just our original matrix R. So we AND those masks to the 3's and 4's matrices. And both of these matrices contributes to the next generation. So if we OR them together, and disclose the result instead of printing, we see a simple matrix for the next generation of the game of life. So here we have a single array expression for the next generation. You'll notice that the size of the matrix R is not specified anywhere, so that the expression is applicable to a matrix of any size. Let's extract it as a function by replacing all occurrences of R with a formal parameter O, and call it the function life. Let's test it. There are the first 3 generations. We can abstract this progression by making function gen for generation, which is life to the power of the right argument applied to the left argument. So R bound to gen applied to each of the first 4 numbers gives us 4 generations. Next, let's make a larger arena still. So RR is the 15 by 35 take of R, rotated by 1020. This is a 15 by 35 matrix of zeros and ones with our original R in the center. It's easier to see this if it is plotted as an image. So we make a picture with squares corresponding to the zeros and ones in RR. Open a display window for this so that it can be seen, and show the pic. Finally, make an animation to show it working. All we have to do is apply the life function and the power limit to the original population. The power limit finds a fixed point of its operand function life by applying it successfully to generations until the result and argument are identical. This is not a closure function, so it is implemented in our own library function. We will wrap the life function in an outer function where we won't change anything, except it gives the opportunity to introduce a side effect of updating the picture in the window with the image built from the argument to the function that is applied by the fixed point operation. Changes in this image will be reflected in the display window, so we should see it working. We want just two small refinements. First, we're not interested in the result of the power limit, so we can wrap in a do nil to discard it. Second, to have a chance of seeing it working, we need to apply a small time delay, so we will include 1/8 of a second, or 125 milliseconds. There we see it running. The way we've coded it with rotations, we've produced life on a torus, so the edges wrap. So there you are. Life in Clojure.